Okay, let's discuss a generalization of Newton's law of gravity and introduce the gravitational field, which you all probably just call gravity, but actually the gravitational field, as we will see, is dependent on a planet's mass and radius. So, and that g, little g, is actually an acceleration due to gravity, correct? Now, let's consider the following situation. If we put a mass, and you all use the mass, use a box a lot of times as a mass to depict a mass of an object resting on the surface of the Earth right here, m sub 0. Now, previously you would just say that that box had a weight. The object has a weight given by its mass times the acceleration due to gravity. Now we should know that that force, the force of weight, the weight force, is actually supplied by the gravitational force. This equation here, big G times the product of the mass of the Earth and the mass of the object over the radius of the Earth squared, because the object is sitting on the surface of the Earth. So that the radius here is the radius of the Earth. Now, so what's the physics? We see that the weight force is supplied by the gravitational force. Now, notice that right there I need a m sub 0 for object mass. I don't have that right here. So let's do that to make sure I have my notation correct. There we go. Okay. Now, so let's set those two things equal to each other, the gravitational force and the weight force. When you do that, notice that the object mass cancels. And that tells you what you should know from the first semester, that free fall due to gravity, any object that's accelerating near the surface of the Earth, all objects accelerate at the same rate if we ignore friction. If we ignore friction, for example, in a vacuum, a feather and a bowling ball will fall at the same rate. Now, there's a really cool video showing that. You can look it up on YouTube. Feather versus bowling ball in a vacuum. Now, if you look at this equation and solve for little g, the acceleration due to gravity, and let's call it gravity on Earth because we're talking about Earth over here, you see that the acceleration due to gravity is equal to big G, the universal constant, 6.67 times 10 to the minus 11, times the mass of the Earth over the radius of the Earth squared. So we can generalize this to any planet. The acceleration due to gravity on any planet is, once again, that constant, big G, times the mass of the planet over the radius of the planet squared. So the acceleration due to gravity on any celestial object, and for example planets, would depend on the planet's mass and radius. And explicitly, it's directly proportional to the mass. See that? Directly proportional to the mass of the planet, and inversely proportional to the radius squared. So that's how the law of gravity works, and that explains, like we could call little g a gravitational field associated with a planet. Okay, now let's generalize this law away from the surface of the Earth at any height h, at any altitude. That's altitude, a distance from the surface of the Earth. Okay, now generally with h being altitude above the Earth's surface, we need to make a correction for the radius of the Earth here and just add to it the height, because notice that now, because we have to measure this force from the center of the planet. So from here to here is our new radius. So we just need to add the altitude to the radius of the Earth and then square it. Be careful there. You got to add the altitude to the radius of the Earth or some planet and then square it. So there's a generalized formula for the acceleration due to gravity on the Earth, and we could replace that E with P's, and we would have G on any planet would just be the mass of the planet over the radius of that planet plus some altitude from that planet's surface squared. Now why is it that in the first semester you all just use G was a constant? Why is that? Always you use G as constant. Well, it's because at the surface of the Earth, of course, h is 0. However, even if you're on the highest mountain on Earth, the highest mountain on Earth, that height is still very, very, very much smaller than the radius of the Earth. So essentially, for most problems, it's a very good approximation to just assume h is 0. You've got to be pretty far out. That altitude, you have to be way out in space almost for this to be significant. Okay, now, so that, like I said, so making g constant is a very good approximation for a lot of problems, like in kinematics. Okay, now let's look a little bit closer at this. This depicts a vector field associated with little g. That's what g looks like if we depict it with some vectors. And notice that these vectors, the farther they are, like if here's a surface associated with those little spheres at some altitude above the Earth. Notice that those vectors are bigger than, say, these vectors. Why is that? Because gravity is getting weaker as we move farther from the Earth, right? So we see the vectors getting smaller. And this direction defines down. No matter where you are, that is down, right? Because that's the force of gravity. It's pointing toward the center of the Earth. Now, how do we experience gravity? It's due to our inner ear, and I have a comment here. You can read that. But basically, your inner ear is filled with a fluid, and it senses motion and gravity, acceleration. So, basically, and something really interesting is that in Einstein's theory of gravity, one of his postulates is that you cannot do any experiment that will discriminate between an accelerating reference frame and a gravitational field. In other words, if you were in a rocket ship and you were moving, if you were accelerating in that rocket ship at 9.8 meters per second squared, it would feel like you were just standing on the surface of the Earth. So that's kind of interesting. But anyway, let's look at what you were doing in the first semester when you used g's constant. Think about it. Here's a human right here, and we would just be an infinitesimal speck compared to the Earth. The Earth is huge, right? I mean, you wouldn't be able to see the speck. And so basically this curvature here in our local, what we can see is just flat. If we ignore any undulations from hills and valleys, it's just a flat Earth as far as we can see. So these vectors that they have something called divergence, and actually that's convergence. And later on, we're going to see that this kind of field's associated with a negative charge in electricity. This would be a sink. For instance, masses are always attracted to one another. There's no such thing as a plus-minus mass. Like, later on when we study electricity, we're going to find that there's a plus charge and a minus charge. And like charges repel and unlike charges attract. Well, for mass, there's only one flavor of mass. It's always attractive. So we depict this field as a sink. Any other mass in that vicinity is going to be attracted to it. So once again, here's a human, and we would be really tiny. So if you think about this curvature, we can't see that curvature, so we approximate it as flat, and these arrows for the gravitational field are uniform. And that is the assumption that g is a constant. So I hope you get the idea of what I'm talking about here. But anyway, it's good to see the vector nature of the gravitational field, because we're going to have to deal with this when we get to when we start in the next chapter when we study electricity. And in fact, we're going to find that where we start in our studies of electricity is a law that looks just like this. Instead of being the law of gravity, it's Coulomb's law for electricity, and it looks very similar to this. We just replace the constant g with another constant k, and we replace masses with charge, so that the law will look very similar. And we need to kind of understand these ideas as we move forward. Okay, that's all. Thank you. Have a good day.